polymorphism or allotropy, right? What is it? Polymorphism or allotropy. We know that some metal as well as non-metal, they have more than one crystal structure, right? So we discussed even this in the introduction to material science, that there are materials, they have more than one crystal structure. And this phenomena is known as polymorphism. Now, when the one and more crystal structure, if this phenomena is found in the elemental solid, only in the solid, the element, then we call it the allotropy. Now you see here, look into the figure. Here we have the carbon, the allotropes of carbon. We have graphite, we have diamond, we have fluorine. So, and we also have the graphene also for the carbon, right? So these are the same material. It is same carbon, but different crystal structure. And based on the crystal structure, you know the properties of graphite is much more different than the diamond. Like diamond is the hardest known material on the earth, and graphite is soft. But they are the same, right? It is same carbon, but because of the different crystal structure, they have different properties. Now the prevailing crystal structure depends both on temperature and external pressure. So if the temperature, we are changing the temperature, or we change the external pressure on the material, the crystal structure might change. Now here is the example of iron. So for the iron system, what we have, if we increase the temperature for the iron, so at 912 degrees centigrade, the iron behave as BCC crystal structure. And at 1394, it behaves like FCC crystal structure. And if we melt it, like the temperature reaches to 1538 degree, which is the melting point of iron, so then it convert back to the body center cube because of changing the temperature. So if we are changing the temperature or external pressure, so the crystal structure of metals changes, right? So one familiar example is the carbon graphite, as I told you, it is written here, and then we have the iron. So what happens to the iron, right? So this phenomena is known as what? This is known as polymorphism. Now coming back to our crystal systems, we discussed in the last class different aspects of the crystal system. But if we take a unit cell, right, or when we want to study the material, the crystal system of the material, or as an engineer, if you want to discuss something with the people like who are dealing with the gems, who are dealing with the crystals, so there are some specific parameter, some fixed thing with the help of which we can recognize that where is the atom located specially, or how the atoms are arranged, where exactly in the unit cell there is space, right? All these things. If we want to pass the X-rays or the rays from the material, will it pass, will it reflect, will it refract? For all these things, we need to know the exact location of the atom, the exact location of some certain arrangement of atom within the material, or within the unit cell, or within the crystal system. So for that, we study this thing, right? The crystal system. So a simple cube, which we discussed, has 6 parameters. So as you see here, it is written because there are many different possible crystal structure. So it is sometimes convenient to divide them into groups according to the unit cell configuration and atomic arrangement. Now, one such scheme is based on the unit cell geometry. So here we see this is the unit cell geometry. Now within this geometry, what we have a coordinate system, X, Y, Z coordinate system. If you look here, we have the X axis here, the Y axis here, and the Z axis here. We have the coordinate system here, which is established with its origin at one of the unit cell corner. Now this coordinate system, we have to fix it at one of the unit cell. Now you know this is a single unit cell, but the whole material has a lot of unit cell, right? So if we want to study, we can fix it here at this corner or even in this corner, it depends, we will do, or we have more, so at any corner we can fix it, right? Now the unit cell geometry is this geometry for this unit cell. How we can define? We can define completely this geometry with 6 different parameters. And what are those 6 different parameters? We have the 3 sides. A, this is the A, side B, side C, and we have the 3 angles. The alpha, this is the angle between Z axis and Y axis. We have beta, which is the angle between X and Z axis, and the angle between X and Y is gamma. So the unit cell geometry is completely defined by 6 parameters, and in which we have the 3 sides and the 3 angles. These are indicated here in the figure you see, and sometimes these parameters are termed as lattice parameter of a crystal structure. right? So these 6 parameters we will use in today's lecture. Now, based on the parameters, the 6 parameters, what we have different possible combination of sides A, B, C and angle alpha, beta, gamma, each of which represent a unique crystal system. If we have a system in which side A is equal to B and B is not equal to C, this is one system. If we have a system in which all the 3 sides are equal, another crystal system. There might be in which none of them is equal to each other, so that is different crystal system. And we have 7 crystal systems, and those 7 crystal systems are here. You see, we have the cubic, the tetragonal, hexagonal, orthorhombic, rhombohedral, monoclinic, and triclinic. The cubic system, the first one, in which side A equal B and B equal C, right? You have studied math. When A is equal to B and B is equal to C, what does it mean? It means that A is also equal to C, right? This is transitive property in mathematics, and I know you people are good at mathematics, right? So the 3 sides are equal, and the 3 angles are also equal. Alpha is equal to beta, and it is equal to gamma. So this is the highest symmetry, highest degree of symmetry. So it means the simple cubic or the cubic structure is the most symmetrical structure. While we have the last one, the triclinic, which is the least symmetrical, in which we see that A is not equal to B and B is not equal to C, and alpha is not equal to beta and beta is not equal to gamma. Right? So all these crystal structures are here. You can see here in the photo, right? I hope it is clear. Let me zoom it a little bit. Right? Now it is. I think it is seen clear. So we have the first one, the cubic. So in the cubic, you see sides are equal and angles are equal, and all angles are 90 degree. Keep it in mind. All angles are 90 degree in this structure. We have the hexagonal, which we already discussed. You see here in the hexagonal, A is equal to B, but B is not equal to C. How? We have this side A, and let's say this is also A. This chart is B. So A is equal to B, because in the hexagon, what we have, if you study this plane, so we have the triangle, right? 6 triangle. So this side is equal to this side, right? This side is equal to this side. But if you look into the height is not equal to that one. So A is equal to B, but B is not equal to C. And same way, alpha and beta are equal to 90 degree, while gamma is 120 degree. You see here the angle between these two in the corner. You see the corner, this angle, right? This is not 90 degree, while all others are 90, and this is 120. So this system is known as what? Hexagonal. So similarly, we have the tetragonal, in which A is not equal to B, but B is not equal to C, right? It is same like this in terms of side, but if you look into the angle, so angles are all equal, and angles are similar to the cubic structure. So this angle is 90, this is 90, and this one is also 90. All angles are 90 there. So this is a different crystal structure, right? And we have the rhombohedral, or it is also known as the trigonal, in which sides are equal and angles are equal, but they are not 90 degree. The orthorhombic, again, the sides are not equal. This side is not equal to this side, and these two are not equal even to the height, right? In the monoclinic, the sides, none of them is equal, but 2 angles are equal. You see this one is equal to this, but this is at some angle. You see the beta, and this one is not equal to alpha and gamma. While the last one, you see, none of the angle is equal to 90, and none of the side is equal to each other. So these 7 different systems we have, right, based on the 6 parameters. Clear? Any confusion? Okay. Now what we have the point coordinate system. The point coordinate system means if we want to locate a point, so point can be an atom for us or a part of an atom. So in a unit cell, the unit cell might be cubic, it might be rhombohedral, it might be triclinic, it might be hexagonal, and we want to point out that where this atom is located. So for that we use the point coordinate system. So a point coordinates is a lattice position in a unit cell. So determined as a frictional multiple of A, B, C unit cell edge length. Frictional multiples of A, B, C, what does it mean? If we have a point located here, so it means, let's say it is located at half A, right? This is A. A is full, A is one side of the cube. Keep it in mind, A, what does A mean? A means one complete side of the cube. B means another complete side of the cube. And C means the third complete side of the cube. So half A means half side of the cube. And why we are putting A, B, C? Because we want to generalize the system. In some metal, let's say we want to study, let's say iron, right? In iron, let's say this side A of the unit cell is equal to 20 nanometer, right? So then half of A will be what? 10 nanometer, right? So that's why we are just putting A, B, C to generalize the system for any atom or any metal we can use it later, right? So here is the example. And in the example, what does it say? We have an atom, this red one, in the unit cell. We want to point the coordinate and we want to represent it. So there is a way of representation for these points, how we represent. So in the example, you see unit cell upper corner. This is the upper corner of the unit cell, this one. We want to represent. So look, if we take the origin of the coordinate system, this is the origin, 0, 0. Now tell me, this point is how much far in A side? One complete A, good. And how much far in B? 1. And in Z? Also 1, right? Very good. Why? Look here. This is here at this corner. So it is, if we go in the A, so it is complete A. In the B, again, it is complete B. Here you see. And in the Z, if you go from here even, it is complete Z. So it means we have complete A, we have complete B, and we have complete C. We don't know what is A, B, C, depends on the material. It can be 10 nanometer, it can be 20 nanometer, right? It depends from material to material. Now this A, B, C, we want to remove the A, B, C, and we want number. So what we will do, I will divide the, if let's say this is the whole side A, so I will divide A by A, B by B, C by C. So I get 1, 1, 1. So point coordinates for a unit cell corner are 1, 1, 1. Now keep it in mind, this 1, 1, 1, it is the point coordinate and the representation is, it is simple 1, 1, 1. We are not closing it in brackets or in or this type of brackets or in the angle brackets. We are not closing it, right? So point coordinate is only 1, 1, 1. Now why I am saying this, these are important. In coming slides we will discuss, right? We want to represent some other thing with this. So the point coordinates is just simple writing the coordinate system 1, 1, 1. Is it clear? Now here is the example. This is I have taken from the book. The another one I took from somewhere else. But look here, the process which I explained you is written here. But here is an example. In the example, they have a point. In a cube cell, they have a point P. And P is exactly at the center of the cube cell. Imagine 3D box, right? And in the center, in this air, there is a point, or there is a ball, or there is atom, whatever is it. We want to find the coordinate system, the point coordinates for that one. So look, what does it say? We have this complete side A, this complete side B, and this complete side C. Now they have another thing. It says that QRS. What is QRS? This is just a general number, means in A side, it is how much away? Q. In B side, it is how much away? R. And in C side, it is how much away? S. Right? So QRS, this QRS can be, let's say, half, 1/3, or again, half, whatever. It can be any number. So Q of what? QA. Q of A. Right? R, you can say half of A. Or R of what? B. Or you can say, let's say if it is away 3/4, let's say 3/4 of B. Whatever is the distance we will say. So this point, the point P, we represent how? We represent by Q, R, S. This is the points coordinate system for the point located in the center of a cube. Clear? Is it easy? It's easy, right? Here we have now an example. Look into the example. What does it say? For the unit cell shown in the figure, locate the point having the coordinate system 1/4, 1 and 1/2. We want to locate a point, right? And which has the coordinate system 1/4, 1 and 1/2. Now 1/4 means what? Can you tell me? What does 1/4 mean? 0.25 A, yes, right? But A here is how much? Here we don't have A, right? So A is now, it is given, the length is given. A is 0.48 nanometer. B is equal to 0.46 nanometer. And C is equal to 0.4 nanometer. So by this coordinate system, 1 by 4, what do I mean? 1 by 4 of A. So what is A? 1 by 4 multiplied by A. A is 0.48, right? So whatever number you get, you will draw here. Let's say that number is, let's say here, right? So I just draw that one here. Now for B, it is 1 multiplied by B. B is 0.46. So just directly multiply with 0.46 and you will get the number, which is again, it will be 0.46. So means B will be where? Here. So from here, we will go up till here, right? Full B. Right? So from here we start and we reach to point B. Now for C, it is half C. So half, and C is what? 0.4 multiplied by 0.40 nanometer. And it might become 0.20. So means half. So now we will go up in C, half. So here there is a point. So the point coordinates for this point is this one, you see. This is the point and this is the point coordinate. Is it clear? It is easy, right? Just to point or show a point in the coordinate system. Here is the answer, you see, here is the point P for the question, right? So 0.12, then 0.46 and 0.2. This is the answer. Any confusion to anyone? Guys, are you with me? Everyone, please type. Yes. So here we have specified the point coordinates for all atoms for a BCC unit cell. Now in the BCC unit cell, we have different atoms, right? So 9 atoms are there. Not 9 complete atoms, but 9 some of the parts of the atom. But in the reduced hard sphere, we show that there are 9 atoms, right? 9 points. So for 9 points, we want to show the location. So let me make a table. And we have 9. So 1, 2, 3, 4, 5, 6, 7, 8. And let's say here is 9. So 1, 2, 3, 4. Yeah, this is. So here what we have the point number. Let's say the point number 1, right? This one. So here is the number. Here we have A, B, and C. Yeah, these are enough. So tell me, for point 1, what will be the coordinate system? 0, 0, 0, right? For point 2, 1, 0, 0, 1, 0. Sorry, this is point 2, 3, 4, 5, 6, 7, 8. Okay, so this will be 1, 0, 0. For point 3, we have 1, 1, and 0. Very good. For point 4, 0, 1, 0, right? For point 5, we have half, half, and half, right? For point 6, 0, 0, 1. Very good. 7, 7 and 1, 0, 1. 8, 1, 1, 1. And finally the 9 is 0, 1, and 1. 9, right? So this is how we locate the points in the unit cell, right? Now keep it in mind, you might have an example in which I will say, let's say A is equal to 3, B is equal to, where is B? A. This is B, they show with A, right? This is B. So, and this is here, okay, this is a unit cell, so they say every side is equal, right? But we have this one A for representation, we have B, and this one is C. right? But all of them are equal because this is a unit cell, that's why. So you can have A equal to 3, B equal to let's say 5, and C equal to let's say 4. So any different structure, right? That will not be a cubic. So what you will do, then you multiply this number with the value, right? To find where is, how much it is far in that axis, right? Or on that side. So this is how we specify the points coordinates, right? For a BCC unit cell. Is it clear? Any confusion to anyone? Here is the answer. You can see here. So finally you will write in this way, right? This is the final answer. The representation is this way. X-axis, Y-axis, Z-axis, and we have like this. There is no brackets, no commas in between, nothing is here, right? Now another thing. The crystallographic direction. What is crystallographic direction? We finish the points coordinates, but if a point is located somewhere and we want to show that from the origin in which direction it is there. So we have to show the direction. And this we can use for different things. Like we see, let's suppose there is symmetry and we see in which direction there is a symmetry in the crystal. Or maybe there is symmetry up to some point and then there is no. So we see up till how much there is symmetry and then there is. So or to look at the atoms. So what we do in the crystallographic direction is defined as a line between 2 points or vector. So the following steps are used to determine the 3 directional indices. 3 directional indices in the x-axis, and the y-axis, and the z-axis. We use these steps. So the steps are what? Wherever there is a point, right? Let's say we have this point. So we have to locate the point and then draw a vector from the origin to that point. Right? All these, it is written here. I will explain this in the example, but you have to read here. Like, and if this is the origin, so this is the positive y-axis, here will be negative y. If this is the positive x-axis, here to back side will be negative. This is the positive z-axis, below it will be negative z-axis. Now, same way we will represent the direction, but with the direction how we represent. The representation is in this way. You see, if it is like this point, and we say that this is 1, 1, 0, the point, right? This point is 1, 1, 0. So from the origin, we will draw a line, but we have to put this one in the square bracket, right? So the representation, the difference between the representation of the points coordinates and the crystallographic direction is the square bracket. Now here there is a possibility that a point, a vector is negative. It is in the negative side. So let's say if we have here the vector. So B is negative, or in the y direction we have negative. So negative can be represented by putting just a bar over the number. So in this, what does it mean? It means 1 is positive and it is 1 complete one side. Again 1 is complete, one side is there, but it is in the negative direction. And then we have 0, 0 is 0. We will solve the example and you will see, right, how it works. Now look here. Determine the indices for the direction shown in this figure. So where is the direction? The green one is the direction. Look here. So for this green direction, what are the indices? What is the representation of the directional indices? You see, this point or this vector is located from origin to the point here. Now this point, how we can represent? What is the point's coordinates for this point? It is 1 over 2 in the A, okay. In the B it is 1, and in Z axis it is 0. Right? So these are the point, the things. Now in the steps, look here. Where there was the steps on the first slide. What we do? Here look, we have X, Y, and Z. This is the same example, right? We know that A was half A. So this is half A, or you can write A over 2. This is same thing, right? Don't be confused. So we have A over 2. Now B side is complete 1. So means 1B. And if you don't write even 1, so still it is B. No need to write. Right? And C is 0, so 0C. Right? 0C means 0. Now what we do? We have the projection in terms of A, B, and C. So in the previous steps, what we have done, we want to remove the A, B, C. So we divide by A, like A by 2, we divide the whole by A, so A will be cancelled with A, and we divide by B, and 0C divided by C. So all these cancel. So we get half, 1 and 0. This is second step. The third step is reduction. What does reduction mean? Reduction means wherever there is a fraction, right, or decimal, we want to remove that one. We don't want fraction, right? Now here you see, where was the fraction? In the first one, which was 1 over 2, 1 and 0. Now there is a fraction in the first one. So how to remove it? We will multiply the whole thing. We cannot multiply only one point, right? We will multiply all three. So if we multiply it with 2, the whole thing, what will happen? This will become 1, this will become 2, and 0 is 0. So it is 1, 2, 0. Now finally we have 1, 2 and 0. So the last step is enclosure or representation. We will put 1, 2, 0 in the square bracket. Now here is one important point. Listen, all of you. What is that important point? With all these crystal systems, we are dealing with unit cell. Keep it in mind, right? Unit cell means every side will be 1, 1, 1. Complete 1 means 100%. This of the side. It can never be 2. Right? 2 means, let's suppose we have the whole 3D crystal structure. So this is a unit cell, and we have another unit cell, let's say here. Right? We have another unit cell here. And there will be another unit cell, right? So we have too much. Now, 2 means we are going from this point to this point, which we are not dealing. We are not studying two cells. We are studying only one unit cell. So sides can never be 2. But whenever you see in the representation 2, it means there is some reduction has been done. Reduction from what? From fraction to integer, to whole number. Right? So keep this in mind. If you have, let's say, 1, 2, 0, it doesn't mean that in one direction, in x it is 1, in y it is going 2. No, 2 is wrong. 2 means there is some reduction has been done. Right? Now, if you have this point, you have 1, 2, 0, and you want to draw the direction. So what you will do? You have to remove the 2. So how to remove the 2? Divide everything by 2. So what you will get? You will get half, 1 and 0. Is it clear, this point? Okay, good. Good. Now here we have example. Draw a direction for this crystallographic representation. We have 1, minus 1 and 0. Now look here, I will try to draw the cube, but I am not that much good at drawing. We have a cube. I will show you the answer. We have the cube here. Let's say this is a cube, right? Somehow it is cube, but anyway. This is the origin, right? This is what? A. This is B. This is C. I want to show which point. Now everything is 1, 1, 1, so we are okay. Now 1, 1, 1 means in x it is 1. In y it is negative 1. So I will go here, this point. And in z it is 0. So means we have this point. Now we are showing the direction, not the point coordinate. So we have to draw a vector from the origin to this point. Clear? And sometimes what we do, look, if we have the whole crystal system, so we are taking this unit cell and this is our origin. But some other guy can come and he say, let's say this is another unit cell here, right? Like here we have another unit cell. Let me somehow draw, right? Let's say here is another unit cell, and he is coming and he want to take this one the origin. If he takes this the origin, how he will draw? Then he will draw within the cube, right? Because for him this is negative and this is positive. But in this case we have this one negative and this one positive. So usually when there is a negative representation or negative direction, or we will discuss in the plane, if some plane is passing from the origin, we relocate the origin. Right? You will see in some example. How we relocate? Look into this problem. If we have this problem, now here is my origin. But I can say, let's say this is my origin. So the direction will be within the unit cell, but it will be in the negative direction because the origin will not be O, the origin will be O dash in this case. Are you understanding, guys? Okay, look. If we have, look here, I will represent here. Ignore these things, I will come to this, but let's say what cube cell we are taking. If we have this one cube cell, right? In the whole system, we are taking this cube cell only. Now here, where is my origin? This is the origin. If I want to draw a direction in the negative, so I will go here, right? In the B axis, let's say. But unit cell means this unit cell is repeating in the whole structure. We can have this another unit cell, right? And this negative and positive, this is another unit cell, right? So if instead of this origin, if you have this origin, so this is the direction. But some other guy can say that this is my origin. So where will be the direction? It will be here. Again, in the same direction, right? If this is the origin. If this is the origin, it is here again. This is what I want to explain. Like, depending on the person, they can change the origin, right? And usually we are changing when we are dealing with the negative direction and when we are dealing with the plane passing from the origin. We relocate the origin because it is the same. If we are taking this one or this one, the unit cell is repeating in the whole crystal system, right? So all the unit cells are same. This is what I was trying to explain here. And here is the answer you see for this one we have here. Here they have not repositioned, but it is okay. We have the negative direction here. Now here the point P is what? It is 1 in A, negative 1 in B, and in Z it is 0. So it is 1, -1 and 0. Clear? Okay. Now here we have some examples. Look here to the example. You will understand it clearly, right? So the first one, what we have a vector, this red color vector you see, and it is 0, 1, 0. Why it is 0, 1, 0? The answer is there, but you have to understand. It is 0, 1, 0 because in the x-axis or in the A direction, it is not going, it is 0. In the Y, it is going 1. You see here? In the Z, it is not going anywhere. That's why this is 0, this is 0, this is 1. So we have 0, 1, 0. Here we have 0, 1, 1. Right? 0, 1, 1. Now 0 means in the A direction it is not coming. In the Y it is coming 1 and in the Z it is coming 1. So we have this point. So we will draw a vector from origin to that point. Clear? Here we have 1, 1, 1. Now 1, 1, 1 means in the X we have 1, in the Y it is 1 and in the Z it is 1. So we have this point. So we draw from the origin to this point. Right? The vector. It is 1, 1, 1. Here we have 0, 2, 1. What does it mean? 0, 2, 1. If there is 2, it means there is some problem, right? And what is that problem? We can divide everyone by 2, so it will be 0, 1 and 1 over 2. 0, 1 and 1 over 2, yes. So 0 in the X, we are not going in the X direction. 1 in the B, we will reach 1 and half in the C. So we reach half here. So and then we draw a vector. Clear? Now look here. We have -2, 1 and 2. So it means if we divide it by 2, so we will get -1, half and 1. Now if this is the origin, so this is +1, you see? This is +1, but we have to represent -1. Now in this case, what has been done? In this case, this thing has been done which I showed you. Now they have shifted the origin from here to here. Here is the origin, right? So here we have -1, half and 1. So go minus in the X direction, -1, right? In the B, go half, and in the C, go 1, complete 1. And then draw from the origin to this point. Now here, this is not the origin, this is the origin. So if we are going in this direction, it will be positive. If we are going in this direction, it will be negative. So this is the relocation of the origin, right? So don't be confused with this point. This here, the relocation of the origin is being done. Now look here to this example. We have -1, 1 and 0. Now if you are dealing with your own coordinate system, forget this line. What you understand, let's say. So -1. Now if this is the origin, so -1 will not be in this direction. It will be somewhere here in the inside direction. But again, if you want to show in the inside direction, so the whole thing will be in the cube behind this cube. Imagine in 3D. So then this cube will be of no use. So remove this cube and bring the behind cube to in front of you. This is what has been done actually, right? This point is a little bit tricky, but I think you understand. Do you understand? Okay, good, good. Then it is good, right? So here is the origin. So -1 and 1 and 0. Here is the origin, here, sorry. Here they have put the origin, not here. If it is here, then in C, how it can be 1? It's C, it is 0, right? So the origin they have put here. So -1 means in the X it is going -1, in the Y it is going +1, and in Z it is 0. So we have this point. So we draw a vector from here to here. Alright? So within the unit cell or within the crystal system, you can relocate the origin. It doesn't matter, right? But you will not count 2. This one is important, like 2, 3, 4. No, we are dealing only with one unit cell because the unit cell is repeating again and again and making the crystal structure. Is it clear, guys? Or you have any confusion? Okay, if it is clear, now related to the origin problem, what we have, if I can have this one origin or this one the origin, so means this line is equal to this line. It will have the same atomic packing factor, right? Or if I want to show this line, it is the same as this line and it is the same as this line. So it means we have some direction which will have the same atomic packing factor or atomic spacing. The atoms will be that much away in every direction. Like we have here, here, or here. Or we can say here, look, this one, and this one. And also this one, right? Because in the same direction, but this is here in this unit cell, this is in this. So here for this one, this is the origin. For this one, this is the origin. So all directions that are crystallographically equivalent means having the same atomic spacing, are indicated by the family of direction. And now the family of direction we can represent with the within the angle bracket. Like let's say family of direction is 1, 0, 0 is like this. Now this 1, 0, 0 means depending on the origin, all combinations possible of 1, 0, 0. What are possible? 1, 0, 1 is possible. Sorry. 0, 1, 0 is possible. 0, 0, 1 is possible. Negative 1, 0, 0 is possible. 0, negative 1, 0 is possible. All these, you see here. So they will have the same crystallography. And we call those as the family of direction because they have the same atomic space. Right? Like someone can represent a point from here to here, and someone, if he takes the origin, this one. So maybe then we will say that according to this, it is negative, but it is the same. Right? In that unit cell, it is the same. So there are 12 members of the family. Like if we have this one family, so we have 12 different members. Right? In the cubic direction. You see here, we represent. In all these directions. You see 3 here, 3 here, 3 here, and 3 here. So same like the points coordinates, we have to represent a single point. Then we discuss the direction. Here we have the plane, right? So how we draw the plane and how we represent it. So these are the steps, but I will explain all these steps with the help of example. You can read it even later for yourself. Here we have example, and with this example I will explain how we are representing a plane, right? Or the Miller indices. Look, here we have a unit cell, cubic unit cell. In this cubic unit cell, we have a plane, the blue one, you see? This is not a single direction, it is complete plane, right? Now this plane, we have to represent it with the help of the Miller indices, and we want to show to which side it is touching, which side it is not touching, right? So from where to where it is, the plane. Now what we need, whenever a plane is passing from the origin, whenever a plane is passing from the origin, we have to relocate the origin, same like the negative direction. But in this case, the origin is here. Is the plane is passing from the origin? No, it is not passing. So the first step, we don't need it, right? No need for the relocation of the origin. Then the intercept. Intercept means which side it is touching and where it is touching. This is important. If you look here, it is touching side point A here. It 1. And it is touching B also. Is it touching point C? No, because it is Aliyah Hilal. Why? How it is touching? C is this one, this one. So is it touching C? This one. No, it is not touching. So it is parallel to the C, right? It is parallel to C. You know, when two lines are parallel, if this is parallel to this line, so where they meet? Never. So when we say never, means at infinity somewhere, right? We don't know. At infinite level. So it means this plane intercept point C at infinity. Means it does not intercept. So we say at infinity. So the intercepts are what? Complete A, B, and infinity C. This is second step, right? The third step is to take the reciprocal. Why we take the reciprocal? To get rid of the infinity. Right? So 1 over A, 1 over B, and 1 over infinity C is the reciprocal. Now why we want to take 1 over infinity as what? 0. So 0 is okay. We have 0. Then we want to normalize, like previously how we did. Normalize means we want to remove A, B, C, and we want to show the exact number. How much it is away in the A direction, how much it is in the B, and how much it is in the C. So for the normalization, we divide this with A, this one with B, and this one with C. So we have A by A, B by B, and C by infinity C. But infinity will become 0, right? 1 over infinity. So what we get from this normalization, we get 1, 1, and 0. Now reduction means if there is a fraction or decimal, we want to make it a full integer, but there is no, so we don't need reduction. We will write just 1, 1, and 0. And the Miller indices are the final, the final plane representation is 1, 1, 0 with this bracket, small bracket. This is how we represent a plane. Again, look, we have a plane here, right? Here is the plane. We want to represent it and we want to show the Miller indices of the plane. So first point in the plane representation, if it is passing from the origin, relocate. Here we don't have that situation, so we don't need this step. The second point is we have to see where it intercept the axis. So it intercept the A at full A, B at full B, and C at infinity. So the next step is we want to take the reciprocal to get rid of the infinity, and we want to normalize to get rid of A, B, C. Just we want to show the integer number, and the final we do the reduction. Reduction means if there is fraction or decimal, we want to make it the full integer, and we have finally enclosure, in the bracket. So we represent the plane like this. Is it clear? Okay. So now we have another plane. Now you tell me, is it passing from the origin? No. Okay, so the first step we don't need. Now it intercepts the XYZ axis where and where. Is it touching the A line? Where it is touching? The C line. No, this C point is not this corner, right? This C is this line. It is written over here, but this is the Z axis, right? So this is A. So touching A, it is touching A, yes. Okay, where? At full A, half A, 0 A, where? Half A. Okay, good. Is it intercepting line, the B axis, the B? No. Is it intercepting the C? No, very good. So what points we have? We have half A, right? B infinity, B and infinity C, right? We have infinity A, infinity B, sorry, infinity B and infinity C and A. So what we will do? We will get rid of the infinity, right? So half A, and this will be, if we divide, right? So it will be 0, B and 0 C, and this will be half, this will be 0, this will be 0 if we divide by A, B, C, right? And finally, if we want to get rid of the friction, so this will be 2 if we multiply with 2, right? 2, 0, 0, and finally the enclosure 2, 0, 0 in the bracket. Is it clear? Here is the solution for this one, right? Look into the solution. It intercepts the first one, the relocation of the origin, we don't need. Sir, I still don't know how we know number by the location of line. How we know number by the location of line. Look, we don't know the number by the location of line. Yeah, this is your question is valid. Now, if it is complete one side of the cube, we know that the complete side of the cube is 100%, right? If you have a box and it has 3 sides, A, B, C, and it is a unit cell, right? Unit cell means each side is equal to 1. So means A is equal to 1. One complete A, right? One complete B is 1, and one complete C is 1. That's why we are bringing 1, 1, 1. That we know. Now this half, I know because of the example, because I know the solution, but if it is not clearly mentioned and your guess is, let's say this is not half, this is 3 by 4, right? Or somebody say it is 1 over 2. So this will not be the case. It will be given to you in the example, everywhere it will be given. But here in this case, I know that it is half, right? It is not mentioned here, but it should be mentioned here that it is half B, right? Half A. For the full 1, 1, 1, that's we know because of the unit cell. Because the whole unit cell, it means every side is 1, right? This is a simple cube unit cell. That's how we are moving to, we are finding the number. Clear, Hussein? Okay, good. So here this half, I know it, right? But if it is in another example, it should be given that it touches A at half, right? Like previously the book example I showed you, it is written. I will show you in the next example, it will be written there, right? So these types of example, I copied from somewhere else, so they did not mention, but it should be there. So here is the representation, right? And the representation, I think I solved this, right? The reduction also we don't need here because it is 2, 0, 0, so fine. And the normalization we put this one. Now we have another plane. Now in this plane, this side, it is touching by, it's 3 by 4, right? It is touching at 3 by 4. And this side is half. So now tell me, which side it is touching? Is it touching A, B, and C? So it is touching all of them, right? So it is touching, and is it passing from the origin? No. So it is not passing from the origin. So it is half A, B is 1B, because B is here, it is touching, right? Complete B. And C is 3 by 4 C. So we have these points. Now can you solve it and tell me the final representation of the plane, the Miller indices? Guys, please. Okay, so how we solve this problem? Look here, we have 1 over 2A, 1B and 3 by 4C. So second step is the reciprocal. We will take the reciprocal. So reciprocal of 1 over 2A is 2A, 1B and 4 by 3C. And then we want to normalize, we want to remove A, B, C. So we will just divide everyone by A, B, C. So we will get 2, 1, 4 by 3. And then I want to get rid of the fraction. So I will multiply every number with 3. So this fraction will finish, right? So if I multiply every number with 3, so what will happen? 6, 3 and 4. And finally I have to enclose it in the bracket. This is the representation of this plane, right? Here is the answer. You see 6, 3, 4. And the steps are given 1, 2, 3, 4, 5, 6. Is it clear, right? Any confusion to anyone? Okay, okay, good. Now we have similarly, like the family of direction we had, we have the family of planes also. As I told you, we don't have a single cube in the crystal system. We have the cube is repeating this cube, right? Here you see we have this one, and this one. Also we have different cubes and they are repeating. So a plane in one cube will be there in the another cube also, and then in the another cube also. So all these planes are similar. This one, and this one. Depending if your origin is this one and you are explaining this one, so maybe the C side is 0. But if you are taking the origin this one and you are showing this plane, so maybe the C is negative. Right? Same here and same here. So we have the plane, family of planes. And example is 1, 0, 0, this plane. And the family we have to represent with this type of bracket. Right? And it will have different planes. This one, all these are same. They have the same atomic packing. Right? The families of plane have the same atomic packing. As I told you in the direction also, they have the same spacing, right? So all these planes are same. And it's known as common crystallographic plane or family of planes. So both are the same thing. Clear? Now we have another example. Determine the Miller indices for the plane shown in the figure A. So this is the figure A. We have to show the Miller indices. Now look into this figure clearly and remind the first step. The first step is if it is passing from the origin, then we have to relocate the origin. Right? And we see that the plane is here touching the origin. To relocate the origin, what we have done? Now this is the origin. But here in that case, what we have done, we have drawn another cube. Right? And that cube you can see here clearly. So now the origin is O dash. Now this is not the origin. So this is the origin. We have relocated the origin. So if this is the origin, then the plane is on this side, on negative side most. Right? Now we have to see which line it is touching and which it is not touching. Look here from this figure. This is the A. Is it touching A? No, so A infinity. B. Is it touching B? Here you see, it is. Right? So this point it touched. And we have C. So C is this line. So this point also it touched. Now it is not a direction that we just show from here to here, right? It is a plane. So plane means if it is touching this point, it should touch the whole, like if we have a B here, we have a B here, let's say we have B here. If you divide it into small b, so all B it is touching, right? And C it is touching here. So this C is also touching, this one also, every C it touch. So that's why the plane is made, right? So then we have the plane, complete plane from here to here, we just combine. If it was a direction, only a direction, so then we would have said that let's say from here go to here or here, right? Depending on the situation. So C it is touching at half. It is not touching full C here. It is touching half here. So C by 2. So this was the intercept. Then we have the, we remove the A, B, C, right? And we have infinity -1 and 1/2. Then we divide everything, like we take the reciprocal to get rid of here the infinity and the friction. So we have 0, -1 and 2. And finally we have 0, -1 and 2. The steps here, they are less steps, but in the previous example, if you see, we have more steps. So these are more detailed, right? So better to do this way. So you can do that problem also with this way, but here you can understand, right? Is any confusion in this plane? Okay. Now construct a plane within a cubic unit cell. Which plane we have to construct? This is a plane. And we have to construct this plane. Right? How to construct this plane? You construct, and then once you finish, you cannot show it to me because I know you will not open the camera. But then I will show you the answer and you will compare your answer with that one. But first, take your time and draw. Now look here. Those who don't know, we have 0, -1 and 1. So 0 means we should understand that it is not touching side A. This is side A. Right? This is A, this is B, and this is C. So it is not touching side A, it is and then we have -1, mean B is -1. So this is our origin, right? So -1 will be on this side. So if we go here, this is, let's say, B -1. Let me make it a little bit far so it is clear. Let's say from here we go, and this is -1, right? And C, it is touching at 1. So C is where? This is C, touching at 1. Now what does it mean? It will not be a single line. Means it's touching B, so the whole B, like this is also touching B here. This B will also be touched. This B will also be touched. This B will also here also. Every B is touching, right? And C, here also it will touch the C. Here also touch C, right? And at this position also it will touch C. So then what we will do? Finally, we will combine these points, right? And it will make a plane, right? So as this Ali Ghafail told that we have a hypotenuse type thing. So this is the plane, right? And this is the way how we draw the plane. All right? Don't be confused. If it is only -B, so -B doesn't mean it is only this one B. The whole line B and the whole cube B will be touching, right? So and let's say if it is positive B, so means if from here we are coming, let's say from here we are coming, so we will not come to this point only. So because this is also B, and if this line is also B, this line is also B, right? This one, every line is B here. So, and this is not touching A, but I'm just showing. If it is from here, so everyone will come to B, right? And then all we will make one plane from this. And then plane can be like this, right? If it is positive B. So this way we construct the plane. All right? If we have the origin, this one is the origin, let's say, and we want to construct a plane, let's say 1, 1, 1 we want to construct, right? So here, +1, B will go, this will be positive, right? Like this way. And if it is not going up in the Z, right? So then this is the plane. So these lines will touch also the A, the ground bottom plane. Is it clear to everyone? The plane, right? We can have a plane like this. Look. If we have, let's say we have a plane, like previously I explained you one thing, which was the A was there, B was 0 and C was 0. So they how we they draw. Look, if A was half, right? So if it is, let's say, half 0 0, so we finally it will be 2 0 0. So if 2 0 0 is given, right? So how we draw? Are we allowed to create another cube in this problem? In that case only when you want to relocate the origin. Otherwise you are not allowed. Let's say if you want to draw 2 0 0. So 2 0 0 is actually half infinity infinity, right? So half is A. So means this is A, right? So if it is touching half A, so this half A is all the way in the cube here, right? And goes up from this point also to this point and to this point. Now is it touching B somewhere? No, B is not touching. C, no, C is not touching. So we will make a plane like this. You see, inside the cube, we put just a wall, right? This is the plane 2 0 0. So similarly, this type you can find a lot of example even in the book and on internet, and you have to practice. This is your homework, right? Practice it. This is very, very important. All these things. For me, it is very easy to put question from these things in the exam. I will just take photo and put it there. So you have to understand, you have to practice. Wherever you face problem, ask me, email me, ask me in the class. I will try to help, right?